Hi everyone, thank you for joining us. We'll be getting started shortly. We're just going to give it one minute just to let everyone in. We've had very high registration numbers today, which is great. As I say, we'll just give it 1 minute, but for those that haven't used Zoom before, down the bottom of your screen there is a Q&A option. You can pop your questions in there at any time and we'll collate the questions and answer as many as we can at the end. The session has been recorded and we'll share that with registrants as well. So if you do find you have joined late and miss any, then you will be sent the recording. As I mentioned, we'll just give it a minute or so and then we'll kick off. Thank you. Hi everyone, just doing another sound check for those that have joined in the last couple of minutes. We will be getting started. I think we'll just give it perhaps another 30 seconds or so and then we'll kick off. Just down the bottom of your screen there's a Q&A section. You can pop your questions in there anytime and we'll answer as many of those as we can at the end. And the session is being recorded as well. We'll make sure that a copy of the recording gets sent to you in the very near future. I think we will perhaps kick off there just due to time, so I'd like to hand over to Jay.
Fantastic. Thank you very much, Holly. Morning, afternoon, everyone, or evening, wherever you're dialing in from. Welcome to today's New Zealand Geotechnical Society webinar on cantilever pole retaining walls. My name is Jay Doddabalapur, and I'm one of the coordinators for the Auckland branch, and I'm joined today by my fellow coordinator, Ben Francis of TNT. Before we begin, please take a moment to locate the Q&A panel. This is along the bottom of the screen. Please feel free to pop in your questions during the webinar, and Ben and I will facilitate the Q&A session at the end, and we'll try to go through as many questions as we can. So today's speaker needs no introduction. Dr. John Wood is the author of NZTA's bestseller, Seismic Design of Bridge Abutments and Retaining Walls, or more popularly known as RRU Bulletin 84. He specializes in bridge design, structural investigations, soil structure interaction, and earthquake engineering. So before setting up his consulting business in 1986, he was head of the Ministry of Works Central Labs. His work included peer reviews of seismic strengthening proposals and seismic risk assessments for hydropower stations. He carried out the bridge strengthening design and peer review for the NZTA and research into earthquake performance of underground structures, retaining walls, and bridge abutments. John is a life member and past president of the NZSEE, and he holds postgraduate degrees in structural and civil engineering from University of Canterbury and Caltech. Over to you, John.
Yeah, thank you, Ben, for that introduction. And good afternoon, everyone, and thank you for joining the webinar. This afternoon, I'm going to summarize some of the information that was published in my Cantilever pole retaining wall paper, published in New Zealand Geotechnical News in June this year. And there should be some follow-up comments. One or two queries that arose from the publication, and some additional comment I hope will be in the December copy of the Geotechnical News. The paper covers at least these 10 points here, and today I'm going to run through most of those topics and just sort of summarize the key factors, I guess, and obviously refer you to the paper if you need more detail, or email me if you have any queries. Now, cantilever pole walls, I've got two photos here. One on the left is sort of about the upper limit of the walls that I'm considering, and the one on the right is a much lower wall down to the lower end of the range. I guess of your wall is less than 1.5 meters high, you might not need engineering calculations for that category. Just a few comments on construction. I don't know whether many of you have been through the construction process, but the first thing you do is you level off your site, do a bit of excavation, then you drill holes for the poles. And on the left photo there, you'll see a 600 diameter auger working its way down into weathered greywacke rock in Wellington. And then once you've got holes, you then insert the poles and backfill the cavity with concrete. Also, we use H5 treated poles as indicated there below the picture. The equipment required is shown here in this photo on the left. Now, this is the equipment used to construct the wall shown on the previous slide, but it's just a medium-sized digger. It drives the auger by its hydraulics. It lifts out the spoil and it deposits it onto the back of a small truck to remove the spoil away. And the almost completed wall that's shown in the previous slides is just shown there on the right. Typical dimensions, I've just listed them on this slide. So we're considering heights from 1.5 up to about 3.5 max. If you go higher than 3.5, cantilever action's not so effective, and you might find that tying the wall with a horizontal rod into a deadman anchor at the top is required. You can still go to heights up over 4 meters, but tieback is probably necessary. Diameter of our H5 treated poles, it's usually 200 to 350, and the concrete encasement 450 to 600 millimeter. The pole spacing is, well, determined by the height of the wall, but normally 1 to 1.5 meters. And it's determined by the height and also the facing. If you use timber facing, typically you'll use 200 by 50 or 200 by 75. And with a high wall at the higher limit, you'll find that you won't be able to span more than about 1 meter without overstressing the facing. But I may not have mentioned the simple rule of thumb. The depth of embedment, LE, is approximately equal to the height of the retaining wall. Obviously, that depends on the soil foundation conditions and the backslope angle. The pile analysis method, which I've described in the paper in some detail, it's the same basic method for all soil types. And I'll come back to it quite a few times, but there are 4 key parts to the analysis. The first stage is to assume failure in the soil as you approach the ultimate capacity of the pile, and then at failure in the soil, the pile rotates in a rigid fashion as depicted in the diagram. So we get, as we approach the ultimate limit load, we get plastic soil behaviour up at ground surface, and then some yielding or plastic behaviour down at the toe. Now, the next stage is to determine the forces acting on the pole, stage 2, and you determine the force acting on the pole at any depth, Z below the surface. The limiting force profile should be based on tests, and that's usually the case. And then once you've got a force profile set up, you sort out the equilibrium equations, you look at the horizontal forces, you look at the moments acting, you set these to 0, you have 2 equilibrium equations. It's a fairly simple matter to solve VC, so with our computer I use Excel, and you can determine, for example, in this case, if you know the horizontal force acting and the eccentricity from the loads on the wall facing, you determine the depth of rotation, ZR, and the total depth of embedment, depicted by L. Now, I've said we're assuming rigid pile behavior. There are two, I think in the paper I give a number of criteria, but two quite straightforward ones that are listed here on this slide. The length over B, and I've used B for diameter here, should be less than 6. And if we look at the encased concrete section, we're usually something 5 or perhaps less. And Guo and Lee had a rather more sophisticated criterion, and probably we should use this one, but they have the ratio of the Young's modulus for the pile divided by the shear modulus of the soil, and that should be greater than a factor times the length over radius for the embedded section of the pole or pile, length over radius to the power of 4. I did a few simple sums and decided that this factor times length over radius to the power of 4 would be typically about 500. And then if we're in reasonable soils and we have a concrete encased pile, the elastic modulus for the pile divided by the shear modulus of the soil is probably of the order of 1,000. So most of our walls should satisfy this criteria. So I think it's reasonable to assume we've got rigid pole behavior. Now, talking about analysis for cohesionless soils, I'm going right back to 1964 to Brahms, and I've copied from his paper this diagram. I think this method, as I understand it, it's been frequently used for pole wall design, particularly minor walls. And so it's worth starting with his analysis procedure. Well, firstly, for the type of pole that we're using in our walls, he assumes rigid behavior depicted by his diagram with the pole rotating, a load applied from our wall facing, in this case, at an eccentricity of E above ground level. And then the next stage, stage 2, limiting force profile. Brahms assumes that the limiting force is 3 times the soil unit weight times the pile diameter and times the depth that you're considering times a Kp. Now, Kp is the Rankine passive pressure coefficient. To simplify his analysis, he assumed that the passive resistance right down at the toe could be represented by a concentrated force. So he set up his equilibrium equation, and he only had one because he could take moments about the toe. And then down here we have his ultimate capacity estimated for the eccentricity and the embedment unfurled. And it's a very simple expression. I'm giving you more complicated ones in the paper, but don't throw this away. It's a useful reality check, and I always sort of put it in at the end of my analysis. I go back to Brahms. The point to note, I guess, on the diagram is the maximum moment at ground level increases quite significantly as you come down, and you can see almost down to halfway down the maximum moment it occurs. Okay, so moving on. And the other method that seems to be quite commonly used for the design of pole walls at the present time is what I call embedded wall theory. And it can be applied to both cohesionless and cohesive soils. Again, I've sort of cheated a little, and I've taken a definition diagram shown here from some course notes that I got from McPender when I went to a course back in 2000. So the embedded wall theory assumes that you've got a continuous wall facing continuous, but that's taken down below ground level. And instead of isolated piles, you assume that the wall is continuous below ground level. The limiting force profile in this case consists of 4 blocks. 1 and 3 are active pressure blocks, and 2 and 4 are passive pressure blocks. And Pender gives an example in his notes. and his active and passive pressure coefficients are just the Rankine ones. He writes his two equations, sigma h, sigma m equals 0, stage 3. He solves them. I mean, he uses CAD, and it's easy doing that. But I quite like Solver and Excel, so that's what I would use. Limitations of the present method. Well, the failure mechanism really, if you look at isolated piles, really involves soil flowing between the piles. And that's quite a different failure mechanism for a continuous and embedded wall. So if you assume a continuous embedded wall, you're off in the direction of the wrong mechanics. Pile spacing effects, well, recent publications or not so recent publications include quite a lot of information about the interaction between closely spaced piles. And there's both test and analytical studies. So if you use this, there's no reason to go to continuous wall theory. And the rotation point assumption, well, that was good for Brahms. He didn't have the computer power that we now have. And so just having one equation to solve was easier. But there's no real reason why we should avoid having our two equilibrium equations and solving them simultaneously. And the other limitation, which I think is quite important to me, I always like to see load versus displacement from zero load out to the ultimate limit state, I guess. Well, displacements are useful for serviceability considerations, and usually you overestimate them, but nevertheless, it's good to have some idea of their magnitude. Now, for going back to the cohesion of soils and going one step further than Brahms, this Guo paper published in 2008, and it's referred to in my published paper, and so you can get the reference details. And I quite like it. It's a very comprehensive paper, a little bit hard to understand, but you can work your way through it. He assumes, well, a rigid pile rotation again, as shown on the left-hand side here, with soil failure at the top, and if you load far enough, soil failure down at the bottom. But he assumes elastic plastic behavior, and so his limiting force profile, if you come down to some depth below the surface and you look at the force displacement curve here at that point, we've plotted force versus displacement. He assumes that it's elastic up to a yield force level, and then the displacement remains constant as you increase the limiting force, or the force on the lateral force on the pile. He considered two cases, just listed up here for the elastic stiffness, both a modulus with a linear increase with depth, and then a modulus that's constant with depth. So this covers a range of different soil types. His limiting force, he has two parts to it, but I've summarized it down at the bottom here. I can't read it on my slide because it's a bit cut off, but it's the limiting force is a function. Well, here it is. This factor AR times the depth and times the pile diameter, and AR is soil unit weight times kp squared. And again, this is the Rankine kp, but instead of having the 3 kp that Brahms used, he uses kp squared based on test results. So okay, that's sort of stage one and stage 1.5. But just looking at his limiting force profiles in a little bit more detail, on my left slide, I've got the pile rotating, the red line showing the displacement of the pile, and the red dot showing the rotation point. Now, depicted in this diagram is the case when we've got soil yield in the upper layers, and then we've just reached soil yield down at the toe, and you get to soil yield here, and then the displacements are not great enough to get you to yield until you get down to the toe. So essentially, this is an elastic zone. And if you keep on loading a bit further, the soil yield zone moves upwards towards the rotation point. And you still have an elastic zone between the shaded areas. Okay, so that's rigid rotation, limiting force profiles, and then he does an equilibrium equations. They're fairly complicated. He solves them, and then he comes up with a cubic equation for Z0. Now Z0, it's cut off on my picture here. I might be able to get rid of that. Oh well, I can probably put that on well, yeah. So I've got rid of the faces. So Z0 is just this depth from the surface down to the point where the level, the maximum level where we get yield in the soil from the surface. I'm not quite sure why he does that, but it's convenient, and he ends up with a cubic equation. It looks a bit formidable, but you can solve it with Excel solver, or you can do it by iteration, and you get your Z0. If you have your Z0, then you can plug it into this equation and get the dimensionless force at toe yield, or also the ground level displacement at toe yield. And we're assuming that you know the length of embedment and the eccentricity of the applied load. Okay, so those are evaluated, and if you're solving the cubic equation, you can actually put in the other equations and solve them. If the elastic constant is constant with depth, you end up with rather simpler equations, and this is the Z0 equation, and no iteration required. You can just plug that one out if you know your E and your L. For design, we're interested in moments in the underground section of the pole, and these expressions here are those for both the constant K and the K increasing with depth. Fairly simple equations. Now, in the paper, I've tried to include quite a few charts so that I envisage that you could do a satisfactory design without going to all those complications of equations and spreadsheets. So on the left-hand side, I've shown the rotation depth versus the load eccentricity ratio. And you need the rotation depth if you want to calculate the displacement of the top of a wall. The equations will give you a displacement at ground level, but you can extrapolate that if you know the rotation depth. And typically for our cohesionless soils, the rotation depth is about 0.75 of the total embedment depth. That's 0.75 meters from the surface. On the right-hand side, I've shown the force capacity at toe yield. I recommend using the toe yield capacity rather than the hyperbolic capacity. And I've shown again for the constant in the Gibson K case, eccentricity ratio, and my dimensionless force at toe yield shown vertically there. So you come in at your eccentricity ratio and you take one or either of these curves or an average depending on the soil that you consider. The constant K gives you a slightly greater capacity. And the good thing about the GLOW method, and I like this very much because I can plot a force displacement curve for my rigid pole. The force displacement curve, this is sort of hidden a bit here, but on my version, but it's a function of this AR and the K0, which is an elastic modulus, and the E over L ratio. So what I'm plotting here is the dimensionless force, the force at any stage of the loading versus a dimensionless ground level displacement. UO is the ground level displacement. So how you might use this, I've just put some numbers in there, but my AR factor, which is gamma times Kp squared, came out at about 150. I estimated for my foundation soil at 20 MPa per metre squared. And I know my loading gives me an EL ratio of 0.15. So I come into my chart, I trundle down to the dimensionless displacement 3.2. I then calculate the actual displacement as 3.2 times AR divided by K0. I've done my arithmetic correctly, it's about 25 millimeters. And if I know the rotation depth, which I illustrated on a previous slide, I can then come in and calculate the top of the wall displacement as being 60 millimeters for this example. Now, these dots are at the total yield capacity, and this one I call the ultimate hyperbolic capacity. To go out to very large displacement, your capacity will increase by about 15%. For cohesive, now moving on to cohesive soils, and I've referred to a paper by Motta, published in 2000, it's covered up, but it's referenced in my paper. The limiting force, he uses the limiting force method, very similar to that I've described for cohesionless soil. So if we go through the 4 steps again, rigid rotation, and then just using some of his diagrams, elastic response to begin with. As you increase the load, you get yield up at the top level, keep on increasing, and then you get yield down at the toe. He assumed elastic plastic response, again, very similar to cohesionless soil. His elastic part of the curve is shown here, and he used the elastic Young's modulus for the soil to define that part of the curve. His limiting force is given by the soil undrained shear strength times the pole or pile diameter times the bearing capacity factor, and I'll describe that a little bit later. Again, like Guo, he assumed uniform or linearly increasing elastic modulus with depth. Now, in the simple version of the Motta or Zhang paper, I use 2 of these papers for cohesive soils. In the simple version of their analysis procedure, they just assume that the limiting force profile is constant down to the rotation point, and then constant at the same value but below the rotation point. And if you do that, you end up with a very simple expression for the ultimate capacity. And this R factor is just simply, well, just look at it here, it's 1 plus the load eccentricity ratio. And your limiting force, as I mentioned on the previous slide, the shear strength, undrained shear strength, pole diameter, and this bearing factor capacity. And you can modify the analysis as Brahms actually did, and you can zoom up at the top. There's a zone of 0 resistance, and if you call that ZT, to get the effective eccentricity, you just add ZT, and to get the effective embedment length, you just take L minus ZT, and you can then still use the same equation with the effective values. Now, again, in the paper, I've presented charts for design. This one just shows for cohesive soils ultimate and toe yield capacities. And the series of black lines, the black full line, black dashed line, are for the case where there's no zone of 0 resistance. And the 2 red lines are for the case where we have a 0 resistance equal to 0.1 times the embedment length. And so this variation in resistance, if you work from the full black line down to the red line, gives you about a 20% variation. So it reduces the ultimate capacity by about 20%. If you look at the ultimate capacity here on the black line, and the black dashed line is the toe yield capacity, there's about a 15% variation. So if you design to tow yield, you'll be acting on the conservative side. Again, a good thing about the model paper, and I've got the year there, 2013, is that you can generate force versus displacement curves. And I've shown a sequence here for various E over L ratios, the red dot being the tow yield capacity, and out up here somewhere we've got the ultimate hyperbolic capacity. The ground level displacement is a function of the limiting force that you assumed, the Young's modulus, the elastic modulus, and the E over L ratio. And you go through the same process that I described previously for the cohesionless cells to estimate a ground level displacement. And now moving onto this bearing capacity factor, which is included in our limiting force profile, this factor here. Gorgidas and others have done finite element analysis and applied plasticity theory to determine what this factor is at a significant depth, so that there are no ground surface effects. And from their analyses, they come up with these numbers. Brahms obviously knew what he was doing. He came up with 9. For a rough pile, it's around about 12. So the amount of roughness or cohesion or adhesion to the pile is a significant factor. Now, in the real world, the bearing capacity factor isn't really uniform with depth. And this paper, which I referred to, and I'll give you a reference at the end, it comes up with a bearing capacity factor related to this expression. So it looks a little bit complicated with an exponential term there. But it starts off at the surface with MPO up at the surface here, and then it has this exponential curve down to the value at depth, or the value that I gave on the previous slide. So for a smooth pile, they're saying, well, it's the green line if you use this equation, and for a rough pile, it's the black line. And our tow depths, if you look at the tow depth, I'm plotting depth versus pile diameter here, and for our cantilever pile walls, we're really in this range. So in the real world, we can expect some variation in this MP factor, but for analysis, simple analysis, and in my paper, I've taken a uniform. And in this paper, again, you'll see the reference in December if it gets that far. I hope it does. Gorgidas and others went a step further. They assumed rigid pile rotation shown here. So step 1, notation's a little different. Z0 is their point of rotation, L their depth of embedment. But this is their limiting force profile with the MP factor varying with depth according to the equation given on the previous slide. And step 3, they look at horizontal and moment equilibrium, and it's a bit more complicated because they've got integration. They integrate the exponential function, and you have to look up your table of integrals to do that. And they do that and then come up with this rather complicated equation, which again you can evaluate on your solver on your Excel and get a Z0. And then once you have Z0, you can plug into their equation for the ultimate capacity. I don't recommend that for design, but in future, if I write any more comments, I'll put a chart with their results on it. In fact, in the December issue, there is a chart with some of their results plotted. For both cohesionless and cohesive soils, I've compared calculated values from the various methods that I've recommended with test values. And I'm showing here the test values, or the ratio of my calculated divided by the test ultimate capacity for a number of rigid pile tests in clay. I found about 77 tests and 17 above my one line. So 17 sort of say that my method isn't conservative, but I think on balance, most of the tests fall below the one line. And my calculated capacities, I should have mentioned that I've used MP equals 9 uniform and an ineffective depth of 0.2 times the embedment depth. And these are more conservative values than I recommend in the paper, but see my comments in the upcoming December issue on that. And the one, and I need geotechnical people in the audience here to help me with this. There's an outlier set of results here. This is Penders and Rogers test in 2015. They're in Auckland clay, and they don't line up with any of the other test results that I've seen. Pile spacing effects. I've plotted some curves here on the left showing the reduction in ultimate capacity or toe yield capacity versus this pile spacing ratio. And the pile spacing ratio is just the spacing center to center divided by the pile diameter, which I'll call B again. The dashed yellow line is from theoretical results at depth. And so that's a bit different from the test results, which are shown by the purple line and the dashed blue line. And for design, I've recommended that out of a spacing, center to center spacing of 5, there's no effect, don't need to allow for it. But if we come into a spacing ratio of 2, there's a 0.75 reduction factor. So for our cantilever pole walls, we should usually reduce by about a factor of 0.8 to allow for interaction between the poles. I don't want to say too much about this. The details are given in my paper, but if I go to this very good reference, Yang, in 2018, he goes through the whole analysis procedure again for a soil that has both cohesion and friction. And his limiting force profile is shown diagrammatically here, but it has a cohesive component and a friction component, and they're written down here. And I've got some ultimate capacity charts, and I've really taken this information from his paper. But there's another parameter that has to be considered, and that's the ratio of the friction part to the cohesive part. And these symbols are defined in the paper. So you can come in at your load eccentricity ratio and read off an ultimate capacity. And I've said, well, in drain clays or weathered rock around Wellington, Grey-Wacky Rock, you might find some of the numbers useful. All the methods that I've looked at and described, and I talk about the lateral capacity of piles in horizontal ground. But of course, if we have a wall, we have quite a step in the ground at the wall face, as shown by my yellow line here, coming to a wall and stepping up. And for cohesionless soils, we've got this effective stress times the depth at which we're looking at the limiting force. So that's really the gravity stress times our kp squared times the diameter. So to find out how this is affected by the presence of the wall, I carried out a finite element, elastic finite element analysis using this unit weight. So if we come out well in front of the wall and come down to a 3 meter depth, I've assumed that we're going to have an embedment depth of around about 3 meters. If we come out here and plug onto the M contour, that's about 60 kPa. But as we get into the wall, that curves up. And if we want to look at the stresses down here, we have to jump to contour K. So in closer to the wall, we get an increase in effective stress or gravity stress. And conversely, if you go out to the other side of the wall and look at a depth of 6 meters, down here we would expect to get 120 kPa. And then as we come into the wall, that contour dives down and we move on to the I contour, which says that we've only got an effective stress, or a gravity stress, I should say, of 100 kPa. In the paper, I summarize this with several graphs. This is one of them here. What I'm plotting vertically is the finite element stress vertical stress divided by the gravity stress at a large distance from the wall. So I'm looking out in front of the wall here. If I come out 2 or 3 pole diameters from the wall, my gravity stress is about 1.3 times that out at a large distance from the wall. And coming in behind the wall, this is on the backfill side. If I come back 2 or 3 diameters, my gravity stress is reduced by about a factor of 0.9 if I'm working from the ground surface on the backfill behind the wall. So looking at various examples on this information, if we calculate our lateral force capacity, assuming level ground, we will be underestimating by a factor of approximately 1.2. Getting towards the end here now, I've looked at the effect of the concrete encasement, and I've done some simple composite section analysis using elastic theory, basically. So this is simple structural mechanics. To do the analysis, well, this is the concrete encasement around the side, and this clear area is the timber pole. I assume a neutral axis location, and then I look at the sum of the forces acting on that section, some of the vertical forces, and I adjust the neutral axis until this sum comes to 0. So I'm looking at compression this side, tension this side. In compression, I've got both concrete and timber, and in tension, I'm only taking the timber. I'm assuming my concrete's cracked. So I went through that analysis for quite a few examples, and then I've ended up with this chart, which is presented in the paper. So if you have a timber pole diameter that's 300 millimeters, and you have 50 millimeter concrete surround, usually you'll have more than that. You can come into my chart and read off the enhancement in the flexural capacity from the composite action. So I'm plotting here flexural strength with encasement over flexural strength with no encasement. And how, I'm probably running through too much time, but how all this will work, I've illustrated with an example on the left, and you can quickly look at the dimensions there. And on the right-hand side, I've plotted depth below ground vertically there, and the bending moment in the composite section below ground. And so from my applied load, I've applied gravity load, the applied load bending moment runs down there. And the key thing to note is that it's down at the peak value, it's about 1.5 times the bending moment at ground. And it's also quite deep down at a depth of over the total embedment length of about 0.4. I suggest that you use the composite section analysis to modify the capacity over a depth of a pile diameter. So this is my capacity at ground level, and then I've increased it because of the encasement effect down to 1 pile diameter. And then my red line is effectively the reduced flexural capacity versus the factored applied moment. Well, you'll probably ask me a question about how will you expect concrete to adhere to a timber pole? Well, I've got an example here. It's one of the few that are around, and it's from these Pender and Roger tests in the Auckland clay. They tested 12 of these piles. Here are some dimensions. They tested them to load, to failure, and then pulled them out. I think they found 1 crack in the 12 sections of encasement. So the adhesion was pretty good in that case. And the final comment in my paper, or the final charts in my paper, are related to water level in the foundation soil for cohesionless soils. Remember that the limiting force is a function of the effective unit weight. And so if we have some depth of water below ground, I'm plotting a depth of water below ground, and I'm plotting my limiting force profile. So the profile changes very much when you get down into water, and the slope of the profile changes. To summarize all that, I've looked at the ultimate capacity with a depth of water varying from 0 to 1 in a dimensionless depth here, the depth of water divided by the total impediment length. And I've plotted horizontally the ratio of the capacity with water present divided by the capacity with water below the depth. So, and you can see sort of if we have water level right up at the surface, we're going to have a capacity of less than half the capacity without any water, and use this curve to get an estimate of what happens when you have water down towards the toe. And then finally, just a few conclusions. I've tried to keep the words rather limited here, but I think the presently used analysis methods have limitations, and we can use recently published methods for isolated paths to provide more satisfactory solutions. I know we don't need great accuracy for these small walls, but I think it's best to head off with the right mechanics to start with. My geomechanics newspaper includes charts that I hope are sufficient for the application of isolated rigid pile theory with sufficient accuracy for design. And the charts cover displacement, pile interaction, gravity stress effects, composite section enhancement, and the influence of the water table. And please contact me on this email address with queries, and I'll be pleased to respond. But thank you. The two references I mentioned as I went through are listed here. I'll like to end at that point. Thank you.
Thank you for the fantastic presentation there, John. Covers quite a lot of the stuff that you'd covered in the paper, which is already a fairly comprehensive one, and sort of sheds quite a lot of light on that. We have a whole heap of questions to go through. Would you like to just catch your breath for a minute and grab a glass of water or something? And I can probably start off.
I've got a cup of water. I've drunk most of it, but I'll have another sip. Well, as you can gather, I'm an old engineer and not too fast at responding to questions, but I'll do what I can. And I suggest that if you contact me by email, I'll lie in bed at night and think about your questions and come back with a good answer the following day. But if you've got some simple questions, fire away at this point and see how I go.
Sure. Right, first one is from Nick Harwood. The budget normally associated with the small scale of the walls being considered does not permit the detailed investigation needed to obtain soil modulus. Is this a case of the sophistication in the analysis being inconsistent with the availability and quality of geotech soil property data? Small scale walls are normally only investigated with hand augers and DCPs.
Yeah, well, I can sort of answer that because one of the slides I showed at the beginning was a wall that was constructed very near to my house, and I was the actual engineer. So what I did is I dug a hole, I augered down quite some distance and established the soil conditions. And then, of course, when we drill the holes, you get a first-class investigation. You see the material that comes out, and you can then alter. You should be able to alter the depth to some degree once you've started augering a hole. So it's true that you won't have a drilling rig on site drilling holes, but for small walls, you can do what I did. Dig a decent hole, doesn't cost much, and then once you start constructing, you'll find out exactly what's there. And you could, once you drill one hole, you could modify the spacing perhaps, or you can drill a bit deeper. Or in the case of my wall there, we dug shallower because the drilling was so hard. But no, it is, and I agree that the analysis does sort of extend a bit beyond the investigation But nevertheless, I still feel that you should use the right mechanics and not oversimplify. And if you take, for example, the rotation point about the base of the pile or pole that Brom's did, in some soils that's unconservative. So, and of course, I like to have a load versus displacement. And it's true that the accuracy of the analysis is not that great, but I still think it's important to do it with the best available mechanics and computational facilities. I hope that answers it. Yeah.
So the next one, can you please touch on lagging design? Oh, this thing keeps jumping here and there. All right. Can you please touch on lagging design? There is some design methods out there where they reduce the design moment by 0.6 to 0.8 for arching effects. Another method is the silo method. Do you have any comment on your preferred method?
So I don't understand the question. You're talking about soil reduction of soil strength? Is that?
Design methods where they reduce the design moments by 60 to 80% for arching effects.
For arching effects?
Yeah.
It's not arching, well, it's not really arching effect, it's interaction of the pressure bulks around the piles. And I'm suggesting that you will reduce by 0.75 to whatever it is, 0.85, somewhere in that range, depending on your pile spacing. That comes from interaction. There, that's for sand. That's a model pile loaded in sand. Can you see that on the slide? Or
yeah.
So there is, work that has been done. Sands or cohesionless material are very difficult to do analytically, but quite a lot of analytical work is being done on clays where you can do finite element and theory of elasticity or theory of plasticity. But this is a test in sand, and you can see the pressures as you load in this way drop off to not very much at 6 diameters, and if you look out to the left, there's a drop off in 2.5 diameters. So I'm saying if you've got a pole spacing of 5 diameters, there's very little interaction. But if you have them closer, then these pressure bulbs interact, and you need to reduce the capacity to allow for that. And that's backed up by quite a number of tests as well. This is a very sophisticated model test. And they had instrumentation on the pile and within the soil.
Yeah, sorry to butt in there. The question was more related to lagging design, John.
To the which
timber lagging, or the panels, the rails, whatever you want to call it.
Oh, okay. So
I'll just repeat the question again. Can you please touch on lagging design? There are some design methods out there where they reduce the design moment by 60 to 80% for arching effects. Another method is the silo method. Do you have any comment on your preferred one?
Okay. No, I just use the I haven't talked about lagging or facing, as I call it, but I just take the gravity stress behind the facing, and well, let's go back to the diagram here. So I just calculate the gravity stress, and well, it's an active pressure because there's sufficient this deflection of the wall. Is well, there's rotation in the foundation, but there's also flexibility in the pole itself. And so we, in design, we assume that we've got active pressures acting, and we assume that they act continuously along the wall without any arching. Is that what people normally do? I mean, that's what I would do.
Yeah, so the tendency there is that depending on what method people are using, that is one way of going about, and the other one is you end up taking your stresses from Wallop or Fru or whichever analysis you're using. So to a certain extent, and yeah, I mean the 60 to 80% is probably again rule of thumb that people have based it on experience.
Yeah. Okay. No, I can't answer that. I don't use those software programs. I'm a sort of spreadsheet man, and well, I do use limit state software for ultimate limit states and things, but for walls, the analysis is pretty simple for these small walls, and I would recommend that you do the hand calculations. I think, and I wouldn't allow for any particular arching. See, although the backfill is not shown in great detail here, normally there would probably be more backfill, and it would normally be a granular free draining backfill. If the failure surface runs into the natural ground, then that's more complicated, and you would have to modify your pressure coefficients for that case.
True.
Yeah, I'm sorry, that's probably not a very complete answer,
but Ryan has your email address if he wants to go for any follow-up questions.
Yeah, send that through to me, and I'll check over more carefully what you've done.
Next one is from Eugene Crestanello. Pole hole spacing strength reduction. Is B1 VM4 really that far off the mark? NZGS recommended for design. 5D is 1.0, 4D is 0.93. He's got a few numbers listed in there. So yeah, I mean, the main question is B1 VM4 really that far off the mark?
Yeah, probably not. They say at 4 diameters, there is no interaction. It's not too bad, but I've looked at a number of different publications, and I've come up with the 5D, and then move in, and as you get closer, you reduce it in, well, I say in approximately linear fashion. So I think the information that I've used is perhaps rather better than B1 VM4. It's not far off the mark. I'm saying 0 out here. I don't know what they say at 4 diameters. It's 0, but it's a small effect at 4 diameters. And as I say, I've looked at other analyses. This is just a summary of what I've done, and I think it'd be a reasonable average. That black line is probably better than anything else that's been published. But again, there's some uncertainty, but for a small wall, I think that's reasonable.
Right. The next one from Gert van de Vorstenbusch is a few years ago, there was some controversy about the adhesion between timber poles and concrete encasement. Can you please comment on that?
The adhesion between concrete and timber?
Yeah.
Yep. Okay. We need more tests, you know. So as I showed those Pender results, well, let's go to that picture again. Yeah, well, they got some very strange results, but the adhesion was very, very good in their case. Yeah, maybe the ground wasn't, it was fairly soft. So, but I remember Mick Pender saying that, oh, if you ever see a pole blown out of the ground and you see them around Wellington, the concrete still sticks to the pole pretty well. So, but also when I did my composite section analysis, I calculated the shear stress on the interface, and that was pretty low. So I decided that the adhesion would be reasonable. Yeah, perhaps all I can say, but we do need more tests of these concrete encased poles. I hope, you know, a master student or someone sets up and looks at this in a bit more detail.
Right. Next one from Doralba Valencia is, when you have a system of terraced walls and given the stress increase with the proximity to the wall, oh, this thing keeps jumping. What can be considered a safe distance between walls to consider them working independently?
Yeah, I haven't really looked at that, but if you go to this paper, it's quite a useful paper in that they look at rigid piles loaded near clay slopes, and so from their information, 5 or 6 diameters away from the clay slope, and there's no reduction in the capacity. I suppose the other thing was to look at this. Oh no, I'm flicking through these, but let's get to this one here. So it's 6 diameters in the front. You're going to get no interaction. So you can probably have your poles a bit closer than that. I have seen a paper, I can't remember the details now, where interaction between 2 walls, it was a particular, it was probably a Chinese construction, but they were excavating between two walls, and they did address that question. So email me and I can perhaps give you a reference which covers this a little bit more clearly. But if you're 5 or 6 diameters away, there won't be much interaction.
The next one from Stefano, currently using as a KA the Rankine KA, and as KP I use Kakwa Creusel with curved failure surfaces, more similar to reality, as Coulomb for KP is too conservative and Rankine underestimates it. Would you agree with this approach? Would you also ignore friction between the wall and soil interface in the seismic case?
Well, answering that last bit of the question, in the seismic case, I always include some friction on the facing. If you've used a good granular backfill, there's no reason why, and against our timber boards, there's no reason why an earthquake that goes to 0. So a conservative estimate is probably a friction factor 1/2 of the backfill friction. And the first part of the question was regarding Coulomb or Rankine.
Yeah, so he's using Rankine KA for your active and Kakwa Creusel for the passive, as Coulomb is too conservative and Rankine also underestimates it. Would you agree with this approach?
Yeah, yes, but with the pole walls, if you design them according to the methods that I've described, they're based on test results. So those KP values are the Rankine values, and you shouldn't be using anything else. Guo carefully looked at test results, and his limiting force is empirical, but it's based on that KP, the Rankine KP. So for the resistance, you use those KP values. For the load on the wall, the active is accurate enough. The Rankine active is enough. And for earthquake load, I use Mononovia KV. And there are modifications. You've got cohesion as well as friction in the backfill. So for the applied load, I would use active pressures based on Rankine. And for the capacity, the passive resistance, I would use, I'd use Rankine again, but that KP squared, which is empirical, but based on pile testing results.
Thank you. Next question from Matthew Hills. How thick can the drainage material backfill be behind the wall before you start designing for the drainage metal versus real ground, say cohesive?
So, I can't answer that very briefly, but let's come back to this diagram. So you can calculate, if you use Rankine for active or Mononovia KB for your earthquake pressures, you can calculate the failure surface. And I'm about to write something up about this. If the failure surface runs through the natural ground, well, quite often there's a lot of cohesion in the natural ground. And so you can analyze for a failure surface running through there or a failure surface running up here. So not much backfill is shown in there, but usually you will have a little bit more than that. I mean, in the example, now let's go back here. See, to build this wall, we had to cut this on a bit of a slope, otherwise it would fail. And so in actual fact, the amount of backfill in here is rather more than shown on this slide. So my backfill on that example runs up like that. And the failure surface is probably running through the backfill, certainly for the gravity load case, but may not be for earthquake. But it is an area of uncertainty. There are, if you email me, I'll give you a very comprehensive, send you details of a very comprehensive paper where a researcher calculated the active pressure forces for a cohesive and a friction soil. So you can, but it's too sophisticated for applying to small walls, I guess.
All right, moving on to the next one. Michael Richardson asks, following on from the question about concrete to timber adhesion, as of 3 years ago, there was little to no industry testing on the capacity of a composite section. Are you aware of any lab testing to confirm assumptions on composite capacity? Pender didn't want to discuss the composite capacity in his testing from 2015, and I'm not aware of anyone taking on this project to get some empirical data.
I don't, there's very limited information, I agree. You know, it was really good if someone in New Zealand, one of the universities, decided to do a little bit more testing on this. All I know is that I have calculated the shear stresses down in this composite section, the interface shear between the pole and the concrete, and the shear stresses are very low, and it's not unreasonable to expect adhesion to work quite well. I can't answer that better. It would be good if someone in the audience got more references on this topic.
Right, we've got another 30 odd questions to go. Are you okay for going for another 5 minutes or so?
Yeah. I'm still sitting here. Yeah.
Okay, so
I'm running out of water, but I've got a mouthful, so I should be good.
Right. The limiting displacements and forces, do they consider the soil structure interaction under concrete encasement or not? How do you define the elastic modulus and shear modulus of soil in case of shallow groundwater table to define soil structure interaction?
Well, that's a hard question. Ask a geotechnical engineer. I'm just a humble civil engineer. In my paper, I've attempted to show, I haven't this afternoon done that, but I have indicated how you might calculate the moduli for various soils. I didn't address the question about how the water would produce the moduli, but typically you don't, you know, for design, you probably don't have to calculate displacements very accurately, and you can, you know, sort of do an upper or a lower bound type of analysis. But at least the information that I've presented allows you to, you know, use your estimates of the soil moduli to estimate what the displacement might be at the top of the wall. email me and I'll think about that one a bit more, but that's about the best I can say at the moment. And look at what I've got on the paper and you might disagree or agree, but I haven't addressed the question of water.
Next question from Matthew Hills. If you do a design using the basic Brom's method versus these methods, what is the practical difference in the final result and real world? Because when you do a design, you just generally grab the next standard length pole, which really pumps up the capacity.
Yeah, well, yeah, you're right to a degree. I mean, I always check Brom's, but nevertheless, I like to think that I'm using the most up-to-date structural mechanics. And I know the input parameters are not well defined, but you know, why use continuous wall theory when you know that's not what happens anyway? And why use Brom's when you know it doesn't rotate about the bottom? And so it's easy enough to do the analysis correctly. And then, sure, but at least you understand the mechanics a little bit better if you do it correctly. And it's not quite true that you just take the available length of pole. You know, in the case of that example that I showed near my house, you're in very hard material, and you don't want to go deeper than you need to, just because you've got a long length of pole. So you know, the contractor will charge you more if you make them go too deep. So there is some economy from doing a reasonable analysis, I believe.
Moving on to the next one. Is there any guidance on the effects of sloping ground behind or footings in front?
Yeah. Well, I referred to there is, but I haven't covered that. But I'll flick through. Let's go to this one. So this Gorgidas and his brother or son or someone and another, they've done this, and it's near clay slope. So they show how the presence of a slope will reduce the capacity. So I would refer you to that paper as a starting point. And if you do a Google search, you'll find one or two other papers, or one or two for cohesionless soils that I came across. But normally footings shouldn't affect it, but the slope will. You know, if you're only a couple of diameters from a slope, then that will reduce the capacity. And you can, as I say from this paper, you can judge. And I think when you get about 5 or 6 diameters away, there's no significant effect of the slope.
Here's an interesting one. How confident are we that the composite interaction with concrete is still appropriate towards the end of the design life, assuming 50 years? Should timber shrinkage and debonding from concrete be considered long-term?
Yeah, good question. I can't answer it really. Well, what I can say is from my own experience, that doesn't happen. Timber, once it's encased with concrete, won't shrink very much, and the concrete shrinks probably more. Again, I can quote from my own house experience. My house is on timber poles encased in concrete, and I was going to build something under the house and excavated a bit, and the concrete still, after my house is 45 years old, it's still adhering very well, and I would need a sledgehammer to break it away. You know, so I think I don't think it's a real issue, but I can't answer that with certainty. It will depend, of course, on the moisture content of the pile when you put it into the ground and or into the ground, and the amount of shrinkage in the concrete versus the amount of shrinkage in the pile. I mean, I suppose these days with limited supplies, the piles might go in a very wet condition, could shrink as much as the concrete, so it could be an issue. But Yeah, I can't answer better than that.
Right, I think we've still got 34 open questions, so I don't think we'll be running through all of them, but maybe I'll probably pop one last one.
Well, carry on a few more if that helps. Just I've got time if that helps. Okay.
How are we doing for time, Holly? Holly, you still there? Silence. Right. Is it common to use these walls where embedment is into rock, i.e. basalt, and how would this change the design approach?
If you're into basalt, I don't really know. In Wellington, into weathered rock, we just drill, but into basalt, you might have trouble drilling holes economically. So you know, there might be another more economical solution. You might just use a concrete cantilever wall if you're on very robust soil foundation material. One advantage of the pole is that you don't need much space to construct it. You know, it doesn't take much space, I suppose. But if you go to a cantilever type concrete, the conventional cantilever concrete wall, you need quite a bit of space behind the wall to construct the concrete cantilever. But I think it depends on how easily you can drill foundation material. Most soils and weathered rock, there's no problem. These diggers with hydraulic drives will go through you know, fairly hard soil.
Okay. There is one really long question, and I think we'll probably close with that one. The question is from Paul Jackson. It's difficult to assess the change in soil stiffness with depth, which doesn't seem to be taken into account with these models. The ZT distance is also a bit of a guess, and Brom's second paper reduces this from his original 1964 one. This affects the point of rotation and therefore the displacement, regardless of which methods are used. It feels like we are using huge simplifications, then determining displacements from these. If we also include the wall displacement factor from the MB guidelines for seismic loading, then the range of input forces are very wide, and the design embedment can also still vary, so much regardless of analysis used. I wonder how much variability there actually is in the actual embedment of walls, and if we should define a suitable SLS head displacement and try to hit that.
Yeah, I agree. There's a lot of uncertainty. Go back and take a step from the beginning. What was the first point, please?
It's difficult to assess the change in soil stiffness with depth, which doesn't seem to be taken into account with these models.
Yeah, well, the models, as I mentioned, the elastic stiffness is certainly taken into account with depth. And both my cohesive soil and my cohesionless soil papers, as I mentioned, consider the elastic modulus varying linearly or constant, and you end up with two sets of curves, and you know, so you can take an average of them, or in some cases the constant modulus might be more appropriate than the linearly varying modulus. So the variation is allowed for to some degree. Certainly the elastic part of the responses. And so the next point that you made is, or question is?
The ZT distance is also a bit of a guess, and Brom's second paper reduces this from his original 1964 one.
Yeah, yeah. So the depth of ineffective is quite a guess, but I then said, well, if you're worried about that, come back to this fairly recent paper, and these curves here show how the NP factor varies with depth, and it's not too difficult to check the simple bronze one against them and do analysis for both, and then use some judgment to decide which might be best for your soil conditions.
And continuing on, this affects the pointer rotation and therefore the displacement, regardless of which methods are used. It feels like we are using huge simplifications and then determining displacements from each.
Yeah, well, I suppose what I've said is that the methods that I'm recommending don't use all the simplifications that we've made in the past. And so with a bit of luck, you should be able to estimate the displacements a little bit more exactly than in the past. At least the analysis methods are not making all the assumptions. The assumption that there's zero resistance over this site can be avoided, I guess. But in any case, the displacements are not often particularly critical for these small walls, are they? Unless you've got some important structure on top, and then you might not even be using a cantilever pole wall for that case. Or so I think you can make a reasonable estimate. And as I say, the design is not too sensitive to how much displacement you estimate up at the top.
So just a bit mindful of time here. So I think let's maybe wrap it up over there, John. Thank you very much. So before we sign off, our next event is the Auckland Branch Christmas Mini Symposium, and it'll be held online all through, 4 Wednesdays through December. Details are in the weekly newsletter, and abstract deadline is soon approaching, so better hurry. We also have Professor Charles Ng from Hong Kong University of Science and Technology presenting on interaction mechanisms between debris flows and multiple barriers, and that's on the 7th of December. So details will follow in due course. And finally, on behalf of the New Zealand Geotechnical Society, I'd like to thank John for taking the time out for this presentation. And I'd like to thank Holly as well from Engineering New Zealand for the IT support. And thank you all for attending. Have a good day. Cheers.
Yeah, thank you. Just contact me on this email address. Those people whose questions I didn't answer or didn't answer satisfactorily, it's a pretty simple address. Just note that and contact me, and I'll give some thought to your questions. Thank you.
Thanks, John. Cheers. Bye-bye.
Bye-bye.